Now, we're going to put everything together to show how we can derive a phase diagram for the multiple energy curves. So let's take a look at this Gibbs diagram at a fixed temperature. On the y-axis, we've got free energy, and on the x-axis, we have composition. Here, at these two extreme points, represents 100% composition of A and 100% composition of B. This curve represents the free energy of alpha, and this curve is the free energy of beta. Tangentially, if we were to draw a straight line through the base of the minimum of both the free energy curves of alpha and beta, this point represents equilibrium points where the chemical potentials are equivalent to each other. Here, in this regime, the alpha phase is the most stable. In this regime, the beta phase is the most stable. Where things get interesting, however, is this region over here between L and M, where both the alpha and beta phase can coexist in different compositional mixtures. For equilibrium between two phases to exist, each component must have the same chemical potential between the two phases. To satisfy this requirement, it requires that the tangents to each free energy curve at the equilibrium compositions lie on a common line. By studying the free energy curves for the different phases at different temperatures, we can construct a phase diagram. So let's see how these free energy curves relate to the phase diagram. So right now, pay attention only to F. This is the complete phase diagram made out of multiple free energy curves. Now I want to show you exactly how T1 relates to the phase diagram. Here, at this temperature, notice that throughout the entire temperature range, the liquid phase has a lower Gibbs free energy than the solid phase and is hence more thermodynamically stable. Therefore, throughout T1, the liquid phase will exist. Now, let's draw our attention to perhaps Tm. Here, Tm represents the melting point from one phase to another. The Gibbs free energy starts off the same, and as the temperature is increased, the liquid phase is more thermodynamically stable with a lower Gibbs free energy, and hence it will exist as temperature increases. At T2, however, things start to get a little bit more interesting. Here at T2, the solid and liquid phase can coexist at a certain temperature range between B and C. And here, at the melting point of B, right here, the Gibbs free energy of the solid phase starts out lower than the liquid phase before it starts to melt over here. And finally, at T3, the Gibbs free energy for the solid phase is lower than the liquid phase throughout the entire temperature range, and hence it will exist in a solid phase. Let's use the same principles for this slightly more complex phase diagram. So consider at first T1, right over here. At T1, the Gibbs free energy of a liquid phase is lower than a solid phase throughout the entire temperature range. Hence, we can expect the liquid phase to be dominant throughout the entire temperature regime. T2 is slightly more interesting. Here at T2, notice we can draw a tangent between the minima of both the solid and liquid phase. That means that in this regime, solid and liquid can coexist. And here, as temperature increases, the liquid phase has a lower Gibbs free energy than the solid phase, and it is hence a liquid. This entire line can be translated here. At T3, things get a little bit more interesting. We actually can draw two tangential lines between the solid and liquid phase free energy curves. Hence, there are two regimes here and here where solid and liquid can exist simultaneously. However, in the middle, this stays in a liquid phase because of its lower Gibbs free energy, and here, it's solid phase. This entire line can be translated here. And we notice that we can do the same for T4 as well, right here, where it stays solid only in this regime and has a mixture of solid and liquid where we can draw a tangential line between the free energy curves. And this, of course, corresponds to this line. Finally, if we were to look at T5 over here, we can draw a tangential line between these two minima, and the mixture will be between alpha 1 and alpha 2 in this phase. So here, in this next example, I wanted to show you exactly how the tangents can represent the different points within the phase diagram. Notice, especially for T3, we can draw a tangent in between all three curves. When we do that, the middle point always corresponds with the eutectic point. Notice also for T4, even though we can draw a curve almost through all three lines, the minimum point is actually between the alpha and beta phase, and hence only the alpha and beta phase can exist even though there is liquid within the free energy curve. So here in this final example, you should be able to relate T1, 2, 3, 4, and 5 directly to this phase diagram. What I did really want to point out to you was perhaps just T1. Even though we've got multiple free energy curves, alpha, beta, and gamma, notice that the free energy curve for liquid has the lowest Gibbs free energy. So no matter where it exists at T1, even though there are free energy curves of alpha, beta, and gamma phases, the liquid phase will be dominant because it is the most thermodynamically stable. And that's it for this lecture. This concludes our lesson on phase diagrams and the Gibbs phase rule.